Hello, my name is Koen. I'm very honored to speak to you today as an SQM agronomist. SQM is a global company with vast experience in specialty plant nutrition management for over 50 years. Myself, I'm speaking to you from Belgium, where we have main offices and operations for the European, Asian and Oceania markets. You can see it here on the map as one of our many offices around the globe. Belgium, by the way, might also be referred to what we call the heart of the potato belt here in Europe, with very intensive production of potatoes, as it is a #1 exporter of processed potatoes around the world. In this aQademy session, I will dig into the production potential and yield components for potato production. And I will discuss the key factors to reach high yield and high quality standards. I will explain this with special attention to nutrition requirements in general and share some insights on how important it is to select the right fertilizer sources to achieve high yield and quality under different conditions. In order to understand the full production potential in a certain area, we have to remind us on the nature of the potato crop. As you can see in this map, which shows in green the most suitable areas for potato production, suitable areas have relatively cool climates and certainly adequate water availability. You find them in important areas of the USA, Mexico, Brazil, Europe, South Africa and Southeast Asia. It can also be said that the potato crop adapts relatively well to a wide range of conditions, witnessed by its global spread during the past centuries. And of course, in more and more areas, potato farmers succeed in gaining more control on managing their conditions. A very illustrative example on managing conditions is demonstrated by some study results shown here. In a study by one of the leading research institutes for potato and vegetables in Europe, a comparison was done at equal nutrient supplies, but under different systems. Rainfed was compared to drip irrigation and drip fertigation during a rather dry season in 2019. Where water availability was properly managed, compared to the rainfed system, yields were clearly more than doubled. Water is not only essential to the process of photoassimilation of dry matter, but is also the main transport medium of essential nutrients via root uptake. When the nutrient availability is more efficiently managed through fertigation compared to only irrigation, we see more than 20% increased net yield in the commercially important above 50 millimeter classes. Knowing that in Belgium less than 5% of the potato fields are fertigated, this demonstrates that there is still clear room for improvement to manage the conditions and increase efficiency of land, water and fertilizer use. Top producing countries around the world reach average productions of around 55 tons per hectare. With more optimum conditions and management, we already see maximum yields up to 100 tons per hectare. Full genetic potential, being the potential when all micro and micro conditions are optimum, are mentioned to be even significantly higher than 100 tons per hectare. So again, it must be clear that there is room for improvement when we manage variety and seed selection, cultural practices, phytosanitary management, water management, and of course, nutrition management as professional as possible. Looking to the development phases of the potato plant during the season, we can clearly understand that the main yield components are the total number of tubers, which relates to the number of plants per hectare and the number of stems per plant, and the tuber weight or tuber size, which is related to dry matter production during photosynthesis and translocation of carbohydrates to the tubers. The main key factors that define the number of tubers and tuber filling are the variety and seed quality, a uniform emergence and good vegetative growth, root development, tuberization, translocation of the sugars to the tubers or tuber filling, the maintenance of the vegetative area, and storage. I will now discuss these key factors and make some links to nutrition management where relevant. The variety selection not only defines the genetic potential, of course, but also if the type of potato matches with the local markets and conditions. The chosen variety defines to a certain extent the vulnerability to conditional stresses like diseases, cold, heat, drought, etc. And the seedling quality in terms of vigor, physiological age and health determine the number of tubers a potato plant potentially will produce, in addition to the tuber weight and total yield it will potentially achieve. Physiologically, mature seeds, tubers, generally have multiple bud breaks and generate a larger number of stems, which contributes to a larger number of tubers per plant. So, be aware to start off with high quality seed if you want to achieve the highest results. The potato plant development is determined by the homogeneity of its emergence. Therefore, high productivity is directly related to a shorter period from planting to emergence, which helps to rapidly initiate the photosynthesis. So, not only adequate physiological age of the seed and pre-bud break, but also precise superficial planting at adequate soil temperature, like above 10 degrees Celsius, accelerate the process of emergence. Related to emergence, I would like to make a first link with nutrition. For the early uptake of nitrogen, it is important to apply an optimal nitrogen source balance. We will explain that the optimum ratio for soil-grown potato is 80% nitric to 20% ammoniacal nitrogen. Nitrate being the natural form in which nitrogen is taken up after nitrification in the soil. Nitrification processes decrease considerably with soil temperatures like below 20 degrees Celsius. So, especially during colder springs, the supply of part of the initial nitrogen as nitrate will allow proper early root nitrogen uptake, even when soil temperatures are still below optimal conditions for nitrification. After emergence, a rapid phase of vegetative growth begins and continues until flowering before to diminish considerably. There is a direct relation between magnitude of root and aerial growth, as proven by Harris in 1992. Also, here there is a relation with nutrient sources. Nitrate nitrogen has a positive effect on the promotion of cytokinin, which stimulate cell division and lateral growth, as shown in the picture of a study by Romheld in 2005. To obtain high yields, the leaf area index must reach around 3 square meters of leaf area per square meter of crop surface as early as possible. Fast development of the canopy is important. Early closure of canopy also influences weed control and prevents drying out of the soil. The amount of intercepted light accounts for 92% of variation in yield in absence of water stress. A maximum root and vegetative growth is needed in the shortest time frame prior to tuberization. A concentrated tuberization period leads to greater homogeneity in tuber size, which is important like for processing industry. Tuberization starts when the stolons begin thickening, usually 5 to 7 weeks after planting or 15 to 40 days after emergence. During this stage, carbohydrates produced in the foliage are utilized for stolon growth and for the initiation of the tuberization, which relates also to the genetics, temperature, soil, moisture, and hormonal status. Short days and low temperatures, especially at night, stimulate early tuber development. But also a concentration increment of the cytokinin hormone level favors the tuberization. A good availability of phosphorus in the soil is fundamental for adequate formation of the root system and, in turn, a greater number of tubers. Also, application of nitrate nitrogen enhances cytokinin formation, as discussed before, while boron and zinc enhance intensive cell division. Nitrogen availability, however, should be in adequate balance with potassium, since excess nitrogen diminishes tuberization and elongates the process, resulting in a non-uniform tuber size. Demand of photoassimilates increases after tuberization during tuber filling. A strong foliage and good root development are needed in order to promote an optimal start of tuber growth. Once carbohydrates are produced, they are transported to the different organs via the flowing. In this process, magnesium, boron, and potassium play a fundamental role. Potassium is the main osmotic regulator of plants, and it directly participates in the stream of photoassimilate via flowing. So the higher the canopy providing photosynthesis assimilates, and the higher the translocation of these assimilates to the tubers, the higher the yield. In the shown picture you can see how a balanced nutritional program can improve the canopy development and hence improve the dry matter buildup. The balanced nutrition will also assure a proper potassium level in a good nitrogen to potassium ratio to improve translocation of the dry matter components to the tubers. The vegetative area should be maintained well. One of the main functions of the photosynthetic system in potatoes is to capture light and harness it for the production of dry matter. As long as the foliar area is active, photosynthesis will occur, leading to greater yield and higher tuber quality. Maximum yield is directly related to net daily photosynthesis. To determine net photosynthesis, the carbohydrates consumed in the respiration process have to be subtracted from the carbohydrates produced in the photosynthesis. All stress affects net photosynthesis. Water stress, temperature stress, salinity stress, pest and disease, light, nutrient deficiencies, and then especially potassium and magnesium deficiency. We should try to avoid or diminish all these stresses to increase the net photosynthesis. Also here I'd like to make another link to the nutrient sources, which is important to understand canopy efficiency. As you will know, magnesium is the central element of the chlorophyll molecules where the first steps of photoassimilation take place. This makes there is a direct link with the magnesium level in the leaves and the dry matter production in the tubers. Magnesium is synergistically taken up more efficiently in an environment where predominantly nitrate nitrogen is present, while the uptake is clearly decreased due to the antagonistic effect with ammonium. High levels of ammonium decrease magnesium uptake. In these figures, you see that the synergistic uptake of magnesium can lead to a triplication of the magnesium content in the dry matter compared to antagonistic uptake. The synergistic uptake mechanism works for all cations and anions. This means that with ammoniacal nitrogen, we cannot achieve the same levels of uptake of potassium and calcium, like we do with higher nitrate nitrogen content in the nutrient solution. So, this defines greatly the tuber filling and peel quality. Also, a nitrate environment will take up less chloride if present in the nutrient solution, since nitrate has an antagonistic effect with chloride, decreasing the vulnerability to storage losses. Let's now focus on the nutrient requirements and fertilizer selection. Of course, potatoes are no different to other plants requiring all essential macro and micronutrients like nitrogen, phosphorus, potassium, calcium, sulfur, magnesium, iron, manganese, boron, zinc, copper, molybdenum. All these nutrients have essential physiological functions as described in these tables, but some of them are required in higher amounts than others. Due to high production potential and the accumulation of starch in the tubers, potato crops require large amounts of nutrients, especially potassium. If you look to the levels of nutrient removal and nutrient accumulation of potatoes, as shown in this table, it becomes immediately clear how important the requirements of potassium and nitrogen are. This makes it even more relevant to supply potassium in combination with nitrate nitrogen to optimize the uptake of both nutrients together, especially during the tuber filling stage. The uptake demand peaks clearly during tuber filling, when potassium is required in high amounts to transport the photoassimilates from the leaves through the phloem to the filling tubers. Now we would like to exemplify how to evaluate the main differences between the nutrient sources. As we saw previously, nitrogen and potassium are the nutrients required in the highest amount by potatoes, so let's use these nutrient sources to highlight the main differences between nitrogen and potassium sources. Let's start with potassium, since it is the nutrient required in the highest amount by potato. Ja, toch. Now we would like to exemplify how to evaluate the main differences between nutrient sources. As we saw previously, nitrogen and potassium are the nutrients required in the highest amount by potato, so let's use these nutrient sources to highlight the main differences between nitrogen and potassium sources. Let's start with potassium, since it is the nutrient required in the highest amount by potato. Potassium is the nutrient required in high amounts because it is involved in many physiological processes. Osmotic processes defining root uptake, regulation of the opening and closing of the stomata, so transpiration, water movement in general, and transport and storage of photoassimilates and starch during tuber filling, as mentioned before. So, a plant with higher efficiency in these processes will result in increased dry matter and yield levels, greater size of tubers, increased resistance to frost and drought, better quality in transport and increased shelf life, better cooking and process quality, and improvement in coloration after frying, for example. If we look to the main potassium sources used in agriculture, shown here as potassium nitrate, potassium sulfate and potassium thiosulfate, and potassium chloride, it is not the potassium itself that makes the difference, since the element potassium is present in the same chemical form in all these sources. But the difference and impact on soil nutrient solution and in the plant will be defined by the counter ion, which is different from these different sources. When potassium nitrate is used as the potassium source, nitrate nitrogen is supplied, When SOP or PTS is applied, sulfate is applied. And with MOP, chloride is applied. Now, chloride, when absorbed in excess by the plant, will lead to toxicity. Common visual symptoms of chloride toxicity are necrosis of leaf margins and tips, typically observed in old leaves first. Chloride can also cause leaf damage when deposited on leaves by overhead irrigation or side dress application. Excessive leaf burn might eventually result in leaf drop and loss of photosynthesis capacity. But even at less visual levels of chloride toxicity, there will be a decrease in photosynthesis efficiency, resulting in lower photoassimilation or photoassimilate production. Chloride that will not be taken up by the roots increase soil salinity, which will affect root development, water and nutrients uptake. No wonder in general, potassium chloride results in a strong decrease in dry matter content and an increase on loss of weight during storage, unlike potassium sources without chloride, with equal amounts of potassium applied. This graph shows the weight losses during storage of 9% in the case of use of potassium chloride and being only 5% in the case of use of potassium nitrate. You see that this is economically very significant, especially for warehouse potatoes. These management considerations to select the right potassium source might indeed help you to increase your economical result. When we use SOP or PTS instead of MOP as the main potassium source, we should also take into account the amount of sulfur supplied together with the potassium. As potato requires high levels of potassium, if we supply all this potassium as SOP, we will also bring higher quantities of sulfur than needed. We should be aware of that in order to keep the balance between the elements and not generate sulfur excess in the soil nutrient solution. A calculation example based on the levels of potassium and sulfur that are exported by a potato harvest show that we bring in an excess with up to 6 to 11 times more sulfur than required by the plant. Some excessive uptake will take place, but the majority of the sulfur will stay in the soil solution, increasing the EC and salinity, diminishing indirectly the uptake of water and nutrients required. On top of this, especially under rather dry conditions, the sulfate might bind with calcium as gypsum, making the calcium fixated and less available. Calcium is already an element which shows reduced uptake under dry conditions, while it is taken up basically via mass flow only. If you make it even more difficult for the calcium to be taken up while creating an environment of excessive sulfate, you will have negative effects on the strength of your plant in general and the strength of the tubers in particular. The downside on the uptake of potassium by the use of SOP should also be seen in another way. As you know, the potassium uptake is really peaking during tuber bulking, so also the availability of potassium should peak then. We will now show you a video comparing the difference between granular SOP and granular potassium nitrate, clearly indicating that the difference between the solubility of these two sources indicate that the peak demand of potassium can only be supported well when the nutrients become easily available. The high solubility and speed of dissolution of the potassium nitrate source is matching the demand. The speed of dissolution of the SOP is not. Let's discuss the impact on the salinity. Although the direct increase on the EC seems rather low in the comparison between a 1 gram per liter solution with SOP at 1.54 and the solution with potassium nitrate at 1.35, however, you should also consider that the nitrate, if applied properly, will be completely taken up by the plant, and And the sulfate, if applied in excess, only partly will be taken up according to the plant requirements. So, the difference in residual EC will impact much more on the salinity status of your soil solution, and you should care on the longer term for your soils, while these excesses might accumulate over time. Besides an effect of excessive sulfate, the use of SOP or PTS as unique potassium source has another indirect impact on the nitrogen sources that you apply. To make this clear, I would like to compare as an example the nutrient balance in a soil-free environment like hydroponics. Just for the required potassium and sulfur amount, and show the impact of these sources on the required nitrogen content and form. As you can see, in hydroponics only a fraction of the nitrogen is required as ammonium, and over 90% is required as nitrate. This is due to the fact that nitrate is the form that is taken up most easily by the roots. In soil-grown potato, it is true that we can afford some higher levels of ammonium, while the bacteria in the soil will nitrificate, at least when the conditions allow to do this well. Studies have shown that also for soil-grown potato, optimum results are achieved when 80% of the nitrogen is supplied as nitrate and 20% as ammonium. So the principle of the use of SOP leading to unbalance of nitrate ammonium remains as shown here. If you take the majority of the potassium required from potassium nitrate, you are able to supply also some of the highly required nitrate content for an efficient cation uptake from soil nutrient solution. Keeping the nitrate-ammonium ratio on top of 80% or 90% as nitrate, some of the potassium can be delivered by SOP to supply the sulfur crop requirement, since SOP is a good source of potassium and sulfur as long as it does not lead to excessive sulfur. In this example, the sulfur demand is supplied from SOP and from magnesium sulfate as a rather standard magnesium source. If we replace potassium nitrate by SOP as unique potassium source, you would see that we create an imbalance. Not only will we exceed the sulfur demand, contributing to unnecessary levels of salinity, we would also not add nitrate and make it more difficult or even impossible to achieve the right nitrate ammonium levels. Nitrate might still be supplied via calcium nitrate or ammonium nitrate, but will not reach to the levels required. And if the extra nitrogen required is supplied as urea or ammonium sulfate, it will strongly change the balance in favor of ammonium, with impact on the pH. Acidification in the root zone can then be expected due to the excess of ammonium. And also antagonistic uptake of cations like calcium, magnesium and potassium will negatively impact yield and quality. The following graph reflects the optimum nitrogen source balance needed for potato in practice. This scientific study conducted in South Africa clearly shows that independent of the dose of nitrogen applied, we see the same picture, where a combination of 80% nitrate, 20% ammonium exceeds clearly the yield levels of 60% nitrate and 40% ammonium, and 60% nitrate and 40% urea. The impact of the nitrogen sources is also reflecting on the quality. As an example, you see here the impact on the dry matter content related to different nitrogen sources. Also, take into account an improved uptake of calcium in synergy with nitrate from potassium nitrate and calcium nitrate, which will lead to a stronger peel, lower vulnerability to bruising, and decreasing storage losses. In fact, the main advantages of the nitrate nitrogen in comparison with ammonium nitrogen can be summarized as follows. No losses by volatilization, good mobility in the soil, reaching the roots easily, being efficiently absorbed directly by the plant, also promoting the absorption of cations due to the synergistic effect. No need to be transformed by nitrifying bacteria, so less dependent on pH, moisture, oxygen, texture, temperature. It is converting in amino acids in the leaves, which is more energy efficient than the conversion from ammonium in the roots. It does not generate pH acidity. It helps to prevent chloride uptake and salinity stress. It is a precursor of cytokinins, generating a higher number of stems and tubers. So, the right sources matter, as we described in this example of potassium and nitrogen sources. In practice, the benefits of the use of potassium nitrate-based nutrition specific for potato production can be summarized as follows. It supports a faster start, while increased uptake of nitrogen and cations lead to a faster root and canopy development. This is especially important in colder conditions when bacterial nitrification rates are low. A better canopy formation, also because nitrate stimulates lateral plant growth, a better root development, and a higher number of tubers. Better tuber filling through more efficient potassium, nitrogen, calcium, magnesium uptake during peak demand. Better storage and processing quality, also thanks to a better potassium and calcium uptake. A better external quality of the tubers and a better internal quality of the tubers. Less reducing sugars. And when it comes to efficiency, we usually see less nitrogen losses and lower residual nitrate by the end of the season, due to efficient uptake of the nitrate nitrogen source when applied properly. And we see reduced salinity buildup due to minimum contribution for chloride and sulfate excess with higher water use efficiency as a result. Now, good nutrition management is not only about the right sources we just discussed, but also about the right rate, the right time, the right place of application, as this is described in the 4R concept developed by the International Plant Nutrition Institute. The right rate should take into account the overall requirements of the different nutrients according to the expected yields, taking into account the reserves from the soil and the water. But the rates also should correspond to the requirements per growth phase. Therefore, there is value in splitting applications. It allows you to correspond better to the requirement at some specific moment in the growth season, like to the peak demand of potassium during tuber filling, when potassium is required at much higher amounts than nitrogen. In fertigation systems, we are usually quite flexible in applying a growth stage specific balance. But under irrigation or rain-fed systems, the best we can do is to split our applications. In practice, split applications increase efficiency. A study in Belgium with 23 trials between 2006 and 2013 showed reduction of nitrogen losses between 6 and 11 kg per hectare. Another experiment in Chile showed 9% yield increase, only by splitting potassium supply between application at planting and at 45 days after planting. So, the right time is important as well, and split applications are advised. The importance of the right place is illustrated by the effect of in-furrow application of granular fertilizer compared to spreaded application, reducing up to another 30 kg per hectare of nitrogen losses, as shown in this study from 2019. I would like to finish by showing the impact of proper nutrition management, applying the right sources at the right time, Just briefly, without explaining all details about the circumstances, for more info you're most welcome to contact one of our local offices or local agronomists. Here you see trial results from Belgium, where we applied potassium nitrate based balanced fertilizers in split application. The programs with more balanced nitrogen to potassium and nitrate to ammonia ratios by the use of potassium nitrate based granular mixes compared to programs based on potassium chloride showed indeed faster start expressed in higher crop heights, resulting in higher yield. In a field experiment with improved balances per phenological stage in Poland in 2020, a faster start was also observed and a higher number of tubers could be assessed. A yield increase was noted by more than 12%, and because of the better storage qualities related to improved potassium and calcium uptake, the net yield difference after 3 months of storage was even 17%. Because of the good tuber filling, the yield increase in the better economical classes above 50 mm was leading to an increase of net income of more than 30%. Note that these results were achieved by replacing only a portion of the potassium from potassium chloride into potassium from potassium nitrate. So we can also advise to shift gradually to better sources, with better timing of application of potassium and nitrogen. These practical results show us that the insights we gathered and shared in this session, and which led us to a better design of balanced fertilizers and a smarter application of them, lead indeed to good results in the potato fields. And remember that under conditions like cold, drought, salinity, and other stresses, the nutrient source selection will be even more critical. And these conditions are often encountered during a growing season in many parts of the world. We hope that these SQM aQademy insights will help you to decide to opt for more balanced nutrition as key management parameter to increase yield and quality in potato. It will help us all to increase efficiency of our natural resources, land, water and nutrients. Thank you for your attention.